So the purpose of this video is to discuss solution stoichiometry, which we've already kind of started doing with our understanding of molarity. But the idea is now we're taking our concepts of stoichiometry, converting between grams and moles and particles and molecules, etc., and applying them to reactions that occur in solution. And the most common way that we'll see this in the lab, which is what we did earlier in the week, is through a titration. So again, a titration, the purpose of a titration is to usually determine the concentration of some substance by titrating it with another substance. And usually, we can do that by determining the concentration of an acid with a base, or we can do it the other way by determining the concentration of a base with an acid. Either way, the stoichiometry of it all is going to be the same. But whenever we're doing titrations, these are all going to be neutralization reactions. And we reviewed in class how to write net ionic equations for neutralization reactions. They always have the same net ionic equation because we're always producing the same two products, water and an ionic salt. So the setup is typically as we've seen here. Like we did in practice before, usually have a flask with some substance in it where you know the volume. Okay? You know the volume what's in here because you measured it out. We also add an indicator which changes color depending on what the pH is. So one of the most common indicators is phenolphthalein, which we notice turned slightly pink once we've reached the end point in our titration. The reason that's happened is because we're adding, base here with a known concentration and volume. We know both of these because we can measure what the volume is initially, and we can measure how much we use up as it's added. We know the concentration of it, and then with a little bit of stoichiometry, we can figure out what is the concentration of this acid. That's the goal. We're trying to figure out the concentration of whatever's in this flask. Again, it can be an acid or a base. Now the reason that is because when you reach something called the end point, okay? The end point, as we referenced in class, occurs at a very specific moment. It's when the moles of acid equal the moles of base. Because essentially what this is saying, since our net ionic equation for a neutralization reaction is this, always, at the end point, the number of moles of H plus equal the moles of OH minus. So like if you have 5 of these and 5 of these, 5 moles of each, you're going to make 5 moles of water. If you have 7 moles of this and 7 moles of this, you'll make 7 moles of water. So if we know that the moles of acid and base have to be equal, we can use that logic to determine concentrations using our good old formula, M1V1 equals M2V2. So this formula is used for two main purposes that you need to know. Number one, for dilutions, which we talked about in the video before in practice, in class, and also for doing titrations. So it's got twofold uses. Let's go ahead and do some practice problems with this. So, example 1, 25 milliliters of HCl with an unknown concentration is neutralized by 23.45 milliliters of 0.12 molar NaOH in a titration. What is the concentration of the NaCl that has been neutralized? So I'm trying to figure out molarity. One thing I want to point out, a little bit of notation. Instead of having to write out the concentration of NaOH, we would write out NaOH in brackets is equal to 0.12 molar. This notation, basically brackets mean the concentration of whatever's inside. In this case, NaOH is 0.12 molar. So we got to be familiar with that notation. We have 25 milliliters of HCl. So basically, we're thinking visually. This means we have a flask. It has some HCl in it, exactly 25.00 milliliters. We have a burette, which has some base in it, which has this exact concentration. And we add this much that gets used up over the course of the titration is 23.45 milliliters. Once that happens, we reach the end point. The color of this, depending on our indicator, changes. We know we're at the end point. So, how can we use this information to solve the problem? Well, we know once we're at the end point, we know that is happening because we've been neutralized. This means you're at the end point. And if we're at the end point, we know that moles of acid equal the moles of base. So now we got to leverage our knowledge of molarity to determine the moles of acid and the moles of base. Well, there's two ways we could do this. I'm going to show you the M1V1 equals M2V2 way first, and then we'll do it the longer way afterwards. We know M1V1 equals M2V2. So now that I have this equation, I just need to plug in my givens. Well, M1V1, let's see, what do I start with? Well, I'm dealing with HCl, so 25 milliliters. So I don't know the concentration, M1, 25 milliliters, equal to M2, which is 0.12, times V2, 23.45. All right, now all I got to do is a little bit of algebra, divide by 25 on both sides. If I go ahead and do the math, I should get an answer of, that should be an M1 equals 0. I'm going to check my sig figs. I should have 2 sig figs here, 0.11 molar. And if I was writing with this notation, I could say the concentration of HCl is 0.11 molar. Boom. So applying our M1V1 equals M2V2 equation to this, that allows us to solve neutralization and titration problems using solution stoichiometry. Let's go ahead and do another problem of the exact same type, but try to solve it in a slightly different way and see what happens. Well, example 2. 10 milliliters of KOH, so this is our base, hydroxide, is neutralized, that means I get to the end point, by 13 milliliters of a 0.5 molar HBr solution. So now, in this case, we have something different going on. We have in our burette, we have HBr. And then in our flask, we have KOH. So this time we're titrating a base with an acid. But guess what? It doesn't matter, because we always know at the end point the same thing is true. The moles of acid always equal, please, I hope you know this by now, the moles of base. So let's do this problem in 2 ways. We'll first do it a little bit longer way, and then we'll do it with the M1V1 equals M2V2, so you can kind of see both ways done. Well, if we know moles of acid equals moles of base, let's go ahead and first figure out our moles of acid. Okay? I know that I have a concentration of 0.5 molar is equal to some number of moles over my volume, 13 milliliters. So I got to convert that to liters, 0.013. If I go ahead and do that, I solve for x, I get 0.0065 moles of acid. So that's how many moles of acid were added from the burette. And I know since I'm at the end point, that must be exactly equal to how many moles of base were inside the flask. So I can just assume that that also equals the moles of base, 0.0065. So what I have here now, if I want to solve for, I'm trying to figure out concentration, the molarity. So the molarity is equal to 0.0065 divided by liters. Well, how many liters of base do I have? Well, I have 10 milliliters, so if I do the math, I divide that by 0.01. That gives me a concentration of 0.65 molar is equal to the concentration of KOH. Boom. So that's kind of the actual chemistry, exact chemistry theory going on with moles of acid and moles of base. Let's prove to see if we get the same thing with M1V1 equals M2V2. So go ahead and try it. See what you get. Alrighty. M1V1 equals M2V2. Let's go ahead and plug in. Well, I have 13 milliliters. So 13. Remember, I don't have to convert to liters because I'm given ml in both. M1, well, how many milliliters? The concentration is 0.5. The molarity 2, we don't know what it is. And the volume 2, we know is 10. So if I go ahead and do the math here, I divide both sides by 10 after multiplying those two together. Oh, voila! Isn't the world beautiful sometimes? You get the same exact answer. 0.65 molar is equal to the concentration of KOH. Boom. Cool. Either way is perfectly valid. This works right now. It is not always going to work. When we get to more complicated problems in our acid-base unit later in the year, that's not going to work because we'll start dealing with polyprotic acids. So instead of having HBr, we'll have something like H2SO4. And now the fact that we have two hydrogens is going to throw things off a little bit. But for now, either way is a totally valid way to solve these two problems. This is what we'll be doing in our lab, where we actually titrate something, and this will be on your upcoming quiz. Let me check one thing. Sig figs. You might be thinking, Shar, there's only one sig fig here. You're absolutely right. So, with sig figs, the correct answer should be 0.7 molar. Correct answer with sig figs.